Okay, so here's my conjecture. 1. Everything travels at speed c. 2. The direction in which an object is traveling at speed c is its direction of time. And 3. An object will remain perpendicular to its direction of time. I will demonstrate to you that there is evidence supporting this conjecture. But before I get to that evidence, I'd like to first talk about my motivation for making this conjecture. So the first thing is that if you look at a photon, there's an electric component and a magnetic component to a photon, and it propagates in a direction that's perpendicular to its component waves. Right, so the direction it's traveling in is actually perpendicular to its electric and magnetic components. So that is the motivation for number 3 in my conjecture, which is an object will remain perpendicular to its direction. The second thing that motivates this conjecture is if you consider the situation of an object falling into a black hole. In the Schwarzschild case, upon crossing the event horizon, the object reaches a speed of c, and the object's direction of travel, the direction it's traveling in, becomes its direction of time. So putting those two together, I thought, well, maybe for a photon, its direction of time is the direction that it's traveling in because it's going in that direction at speed c, which is exactly what happens to an object falling into a black hole once it crosses the event horizon. It reaches that same speed, and all of a sudden its direction of travel becomes its direction of time as well. My evidence for this conjecture, if you will imagine, here is space-time. The 3 dimensions of space are represented by the x-axis, the horizontal axis. The dimension of time is represented by the vertical axis. And we have 2 observers. I like to think of them as rocket ships. We have observer A and observer B that exist in 3-dimensional space. Let's imagine that they have the same length, and they are at rest, at least initially, they're at rest with one another. Right, so this is the situation. I want to caution, this is not Minkowski space. This is just sort of a Euclidean space. Right? We have 3 dimensions of space, 1 dimension of time, and it's flat. Even though they're at rest with respect to one another, they are moving forward in time. Right, so I'm giving them vectors showing that they are moving forward in time, even though in the classical sense we would say that they're actually at rest. And I'm going to assume that they're moving forward in time at a certain speed, so these would be velocity vectors. The velocity of object A moving through time I'm representing as the velocity vector v sub A, and the velocity with which B is moving forward in time I'm representing with v sub B. Right. At the moment in this situation, they're currently at rest, though they are traveling into the future. Right. And my conjecture, number 1, states that the magnitude of these velocity vectors must be equal to c at all times. So the velocity v sub A is equal to c, the magnitude of that velocity is equal to c, and the magnitude of velocity v sub B is also equal to c, which is the speed of light. Conjecture number 2 states that the velocity vector has to be perpendicular to the object's 3-dimensional self. So let's suppose that rocket ship B is going to move to the right away from rocket ship A. So we're going to have rocket ship B moving at a velocity v away from rocket ship A. We're going to assume instantaneous acceleration, so it instantly reaches that velocity v, and I want to see what happens to rocket ship B as it moves away from rocket ship A with velocity v. So its total velocity is not only in space, it's moving to the right in space, but it's also still moving forward in time. So the net total velocity vector will be pointing in this diagonal direction. And I'd like to point out also that by conjecture number 2, the rocket ship will have to actually tilt off of the plane, the 3-dimensional of 3-dimensional space, right? So it'll have to tilt off of the x-axis relative to rocket ship A, because conjecture number 2 states that the rocket ship would have to be perpendicular to the direction in which it's traveling. And the total velocity, the magnitude of velocity v sub b is still equal to c. So conjecture number 1 states that even though rocket ship B is moving to the right at velocity v, it would still have to maintain a total velocity of c, right? That's all objects are moving at the speed of light. So I'd like to assign the symbol theta to represent the angle that the velocity vector is making with respect to the x-axis. And if you take a moment, you can find the cosine of theta, which will be adjacent over hypotenuse, as equaling v divided by c. So keep that in mind because we'll actually use that one over and over and over. So how do we get length contraction from this situation? Well, what you have to do is, from the perspective of rocket ship A, the length it's going to see of rocket ship B will be whatever we get when we project rocket ship B back down to the x-axis. And so L sub 0 would be the rest length, and L is going to be the relativistic length. At the angle between the rocket ship and the x-axis will be 90 minus theta. And so, and in this case, again, we want to use a cosine because the adjacent side that we know is L, the relativistic length, and the hypotenuse here is going to be the rest length, L sub 0. So what we get is that cosine of 90 minus theta is equal to L divided by L sub 0. But cosine of 90 minus theta is just the sine of theta. And so we get the sine of theta is equal to L divided by L sub 0. And then we're going to use this very basic trigonometric identity, sine squared theta plus cosine squared theta equals 1. Substituting in what we know these to be equal to, we'll get L divided by L sub 0 squared plus V divided by C squared equals 1. And we'll subtract the V divided by C squared to the other side and take the square root of both sides, and we get that L divided by L sub 0 is equal to the square root of 1 minus V squared over C squared. And this is length contraction. So this is the formula for length contraction. And you can also similarly get time dilation from this scenario as well. So the amount of time that will pass for rocket ship B relative to rocket ship A will be measured by the vertical dotted line that I have here, and I have it labeled as T. So this will be the time as measured by A. T sub 0, you can think of this as the proper time, or you can think of it as the rest time. We get that sine of theta is opposite over hypotenuse, so we're going to get T divided by T sub 0 for sine of theta. And again, using sine squared theta plus cosine squared theta equals 1. For sine theta, we're plugging in T over T sub 0. For cosine theta, again, we're going to plug in V over C. And again, you solve for the ratio there, and you end up getting that T divided by T sub 0 is equal to the square root of 1 minus V squared over C squared, which again describes the time dilation of special relativity. Okay, so let's take a look at momentum. So here again is the situation. The momentum vector is what we traditionally consider momentum, which is the mass times the velocity vector. So to find the momentum vector, we'll just take the mass times the velocity vector. So if we apply this idea of momentum to rocket ship A, we'll find the momentum of A represented as P sub A by setting it equal to the rest mass in M sub 0 times the velocity vector of A, which is V sub A. So to find the magnitude of the momentum, we'll just take the magnitude of M sub 0 times V sub A, which is just going to give us M sub 0 times C, because the magnitude of the velocity vector is equal to C at all times. The momentum of rocket ship A is given by M sub 0 times C. Also, I want you to note that this was also rocket ship B's initial momentum as well before it moved to the right. So the rocket ship B had the same initial momentum going forward in time. The momentum for rocket ship B, this one's going to be a little more complicated because rocket ship B moved to the right at a velocity of V, and so that added momentum to rocket ship B. So to figure out the rocket ship B's total momentum, we're going to represent that with P sub B. We actually will use the Pythagorean theorem, right? So the momentum of rocket ship B in the spatial direction is given by m times v, right? Just like we're traditionally used to. It has a velocity v, its momentum is m times v. And so I'm going to represent that as P sub x, meaning the momentum in the x direction. The momentum in the time direction, which I'm going to represent as P sub t, has to still equal the momentum that it originally had going in the time direction because of conservation of momentum. So the momentum in the time direction for rocket ship B is going to be m sub 0 times c. Right, and to find the total momentum, P sub B, we will take P sub B squared equals the momentum in the time direction squared plus the momentum in the space direction squared. We'll plug in m sub 0 times c for the momentum in the time direction, and what I'm calling m sub v times v for the momentum in the spatial direction, because I want to be careful here because, so notice the note I have up there, the momentum in the spatial direction, m times v, that m cannot be the rest mass, because if we assumed it was the rest mass and we looked at the Pythagorean theorem, we would find that rocket ship B's total velocity would be greater than c, and it can't exceed that speed. So it must not be the rest mass, it must be something different. So I'm calling it m sub v for the mass of a moving object, the mass given that particular velocity. Right, so we square both of those, we get P sub B squared, the momentum of rocket ship B squared, is equal to the rest mass squared times c squared plus the relativistic mass squared times v squared. And we take the square root of both sides, and we get that the momentum of rocket ship B is given by this formula, the square root of m sub 0 squared c squared plus m sub v squared times v squared. Another way of looking at the momentum for rocket ship B is just to take, because its velocity is still equal to c, the total momentum for rocket ship B would also be the mass of rocket ship B times c, because its velocity is still c altogether, but this mass is not the rest mass, it's the relativistic mass, which I'm labeling m sub v. So plugging that into this formula that we were just looking at a moment ago, we get, in place of the momentum of rocket ship B, we'll have m sub v times c squared, subtract the mv squared times v squared over to the left-hand side, and you can factor out mv squared, and then divide the c squared minus v squared to the other side, and you end up getting this formula, that mv divided by m sub 0 is equal to the square root of 1 over 1 minus v squared over c squared, and this is the formula for relativistic mass. And now let's take a look at energy. So here's what I'm proposing as the definition of energy. The total energy of the rocket ship will be given as the dot product of the momentum with the velocity. If we want to find the energy of rocket ship A, we will take the momentum of rocket ship A, dot that with the velocity of rocket ship A, and an easy formula for determining the value of that is to take the magnitude of the momentum times the magnitude of the velocity times cosine phi, and phi here is going to be equal to 0, which means that cosine of 0 is going to be equal to 1. And as we talked about before, the velocity of rocket ship A is equal to c, and the momentum of rocket ship A is equal to m sub 0 times c. And so we end up retrieving this very famous formula, E equals mc squared, at the energy of rocket ship B. We are going to take the momentum of rocket ship B times the velocity of rocket ship B. We're going to dot those, take a dot product of those two things. And so again, we can find that by taking the magnitude of the momentum for rocket ship B times the magnitude of the velocity for rocket ship B times cosine phi, which again is equal to 0. And so we end up getting cosine of phi is equal to 1. The magnitude of the velocity is still c, because that's part of the conjecture. The speed is always fixed at c. And the momentum, remember we just found a moment ago, is the square root of m sub 0 squared c squared plus mv squared times v squared. And so that's the total energy for rocket ship B. And to get it into the more recognizable form, we'll square both sides to get rid of that square root. So we'll take E squared, which is equal to m sub 0 squared c squared plus mv squared times v squared times c squared. Right? And distributing that c squared, we get the recognizable form for this energy. E squared is equal to the rest mass squared times the speed of light to the fourth power plus the relativistic mass squared times v squared times c squared. And that portion right there, the relativistic mass squared times v squared, is what we traditionally think of as the momentum. So, which I'm calling the spatial momentum in this talk. All right. So if you replace that with P, you get exactly Einstein's formulation for energy. But I'm going to replace it with P sub x because it is just the spatial component of the momentum. E squared equals m sub 0 times c squared, that whole quantity squared, plus P sub x times c squared. Okay, so let's take a look at wavelength. So I'm proposing a generalized formula for the wavelength that gives us the general wavelength of any object. So in this case, let's consider the wavelength of the rocket ship. And so we'll look at the wavelength of rocket ship B, the one that's in motion, and we can find that wavelength by taking this formula for wavelength which has traditionally been applied to photons. So we have the wavelength is equal to h divided by p, where h is Planck's constant, and p is the total momentum. And there's an easy way to derive this and a more difficult way, and I was doing the more difficult way a moment ago, but an easy way to consider this is to remember that the total momentum for rocket ship B could be thought of as m times c, where m has to be the relativistic mass. So we take, which I was denoting with m sub v. So we have m sub v, the relativistic mass, times c as the total momentum for rocket ship B. We plug that in for the momentum. There's a formula that relates the relativistic mass to the rest mass. So we're going to go ahead and use that and replace the relativistic mass with the rest mass. So the relativistic mass is the rest mass times the square root of 1 over 1 minus v squared over c squared. So replacing the relativistic mass with that expression and moving the c over to the other side of the square root, we get the generalized wavelength formula for matter, which is wavelength equals h over the rest mass times c times the square root of 1 over 1 minus v squared over c squared. So you could also write this as the wavelength equals h, Planck's constant, times the square root of 1 minus v squared over c squared, the whole thing divided by the rest mass times c. One case to consider is the case where the velocity is 0. So that'd be the wavelength for rocket ship A, who has a spatial velocity of 0. And if we plug in 0 for v, this reduces down to the wavelength equals h divided by the rest mass times c, which is known as the Compton wavelength. This is the wavelength that rocket ship A has in the time direction. We also can consider the case of deriving the spatial component of the wavelength of rocket ship B. It's headed to the right, and so it's sort of splitting the wavelength into two components. There's a time component still, because it's still heading forward in time slightly, but there's also now a spatial component to the wavelength. And so to find the spatial component of the wavelength, which I'm labeling as lambda sub x, we can find that using the formula h divided by p sub x, meaning we're going to take h divided by the spatial component of the momentum. Right? And when we do that, we can find the spatial component of the momentum by taking the total momentum p and multiplying it by cosine theta. Right? So we plug that in. For the spatial momentum, we'll take p times cosine theta. And I will separate the p from the cosine theta. And so when we have p in the denominator by itself, we get h divided by p. Well, that's just the generalized wavelength formula. And so we get that result again. The generalized wavelength formula is just h times the square root of 1 minus v squared over c squared divided by the rest mass times c. And remember, cosine theta, again, is just v divided by c, so we plug that in as well. And when we multiply those denominators together, we get that the spatial component of the wavelength is h times the square root of 1 minus v squared over c squared divided by the rest mass times v. This is the de Broglie wavelength. Actually, this formulation has a little bit of a problem that I was really stuck on for a long time, which is if rocket ship B moves away from rocket ship A, so that's what you see going on in this first diagram here. It's moving away from rocket ship A at velocity v, and then it decides it wants to return to rocket ship A. So it reaches a point where it wants to turn back around. The problem here is that it will never catch back up to rocket ship A. So it sort of can get back to rocket ship A in terms of its spatial coordinate, but not in the time direction. So because they're both moving at speed c at all times, when rocket ship B goes off to the right and it tries to come back to rocket ship A, well, rocket ship A has just gone completely vertical. It's never going to catch back up to rocket ship A. And that obviously is a problem, that B cannot catch back up to A, because in reality, we can observe this very clearly, that whenever we leave something, we can always return back to it, right? So if I walk away from my friend, I can always go back to my friend. They don't jump up in time where I can never see them again, right? So to overcome this issue, I'm proposing that the direction of time actually curls back around to form a hollow tube. And I don't know, I have no idea what the radius of this tube would be, but in this way, when rocket ship B goes away from rocket ship A keeps moving forward in time at speed c, but it's continually coming back around to where it was before, because the time dimension is circular. So I imagine that the space-time looks like this. It looks sort of like a hollow cylinder. We're on the surface of that cylinder, and the direction of time is going around that cylinder in a circular fashion. So this would allow rocket ship B to return to rocket ship A and still interact with it, even if they're out of phase as they're going around this time dimension. So I imagine the time dimension can't have that big of a radius, because again, we observe that whenever we leave something, we can come back to it and still interact with it, which means it can't be too far away from us in the time direction. The other thing that I think is really interesting, if you accept this speculation, that this has some ramifications for antimatter, right? So it's well known that antimatter is just matter going backwards in time. And antimatter can be thought of as regular matter, but moving backwards in time, which gives it all the sort of reverse properties. So an electron moving backwards in time appears to be positive. Matter goes one way around the cylinder. Antimatter just goes the other way around the cylinder. So it would look as if it was traveling backwards in time, but it's not really traveling into the past. This allows for us to explain antimatter. Antimatter is just regular matter, but it's moving the other way around in the cylinder.